Excellent. So I have just a basic outline of what I was planning to run through with everybody, which is hopefully broad enough to answer most people's questions, but maybe with enough detail that we can decide if you have specific questions, we can review them afterwards. So I want to start by just showing you the resources that we have online so that you can go to those at any time if you have questions. Then I'll show how to run the FFC using the website tool where you upload your own data. Then I'll go through installation and setup of the code so that you can then play with the Python code. We're going to do that in Spyder. And then I'll show how to run the FFC in Spyder. And finally, I'm hoping to spend most of the time showing how you can play around with the parameters that we have in the code. And this is where you can make hydrologic specific changes to the outputs of the FFC depending on the streamflow data you're using. So moving right along, these are all links that you can find online. They actually can all be found from the eFlows website, which I'm sure you've been to. So I'll show how you can get to everything just starting from eFlows. You can see me opening up the internet, right?
Yes.
Everybody, okay, great. So let's go just as if we were opening the front page. Is how does it work takes us to the overall description of the information available on the website. So anything you find there, like the box plots, the metrics just broadly are defined here. And then we also have links to the more specific documentation, which covers all the metrics in the FFC, following along here where I'm navigating through. And you can look at the steps in the code for calculating them. So if you're ever using the code and it's just Greek to you, you can come here to the documentation and hopefully having the steps described one at a time with some English sentences around it will help you out. So first, I just want to make you aware of these resources. The last link I had on that page was where the code repository lives in GitHub. And we'll go to that one in just a few slides when we actually get into the code. So remember these resource links. I'll just send out this basic presentation afterwards, so you'll have them all bookmarked. And so the first thing I wanted to do is just quickly go through a tutorial of how to use the eFlows website to calculate your streamflow metrics. So let's go back to eFlows. If you haven't already created a user profile, you can create one, or I already have mine, so I'll just go right to it. And let's delete this example so I can start from scratch. Okay, I'm going to show how to upload data and then we'll get our results. Just a couple days ago, I downloaded some USGS gauge data for consumness, probably Michigan bar or something. So this sample CSV, we can open it up and take a look. Okay, so here's what the data looks like. We have date, flow, and then our dates column. And let's look here at our requirements. So 2 columns, one has dates, one has flow. We need these exact data headers. So if things aren't working for you, you can first check those headers. The second thing is you want to make sure the dates are in this exact format. And for some reason with Excel on my Mac, it always automatically changes those. So this actually wouldn't run. So we need to go and change this format to match the requirements identically. So we'll go to time, we'll find that date. Find that 4-year format, or 4-digit year, just like this. And so now this will work. And I'm going to save as and make sure it's a CSV. And look, it was going to save as a text file. So make sure if things aren't working for you, you check your date format and you check it's a CSV. You double check those headers 10 times, and then it should probably work for you. So let's choose that file. Here it is on the desktop. It's not the XLSX, it's the CSV. You can give it a name and click upload. So if there's anybody who's been having trouble with this, afterwards you can try following these steps again, and if you're still having trouble, then you can talk to me. We can take a look really quickly at the results we have from here. The DRH, for example, is the dimensionless reference hydrograph. So we can open that up, and what we get is the data as it will look graphed out in a dimensionless reference hydrograph. So we can just take a look really quick, and there we are. That's our 50th percentile flow, and this is across our entire period of record. So you can plot more of these, you can do whatever you want with it. We can also look at the metrics that were produced. So those are in our annual flow results. And here it is for my entire period of record, which is from 1950 all the way to, I think, 2017. And I have results for average annual flow, standard deviation, and all of our functional flow component metrics. And if you need a reminder on the definitions of these metrics, we also have this metrics README, which provides descriptions of each of those metrics in the exact same format as this results file. So here we go. It'll define spring time, spring duration, et cetera, et cetera.
Then Noel, does it fill data for you too? Did I read that? Does it fill missing data? Does it get filled?
Yes, I think that's actually described here really quick. Any gaps in the data will be interpolated.
Okay.
So, yeah, it's kind of use at your own risk. If you have a large enough gap, then you might have some misrepresentation in the flow, but you just have a few dates missing here and there. It should still be pretty convenient for processing. Oh, and I didn't mention, but it does have this water year start date option, and you can actually go and change that on the little calendar. You just always keep it as the California water year by default for 10 times. So is everybody with me on that one? Okay, I'll take the silence as a good thing. Let's move on to the next step, which is installing and using the actual code. So I was talking with Angie before we got started about the simplest method and what we really recommend if you just want to use something to get the code running. You don't want to go in as a developer into all the details. And so Anaconda distribution is a really popular platform that data scientists use to run Python. It's kind of this one-stop shop for everything you need to get a code up and running. So I'll have the link to this. So if you don't already have Anaconda, you can just look it up and download it after this meeting. You just select your correct operating system. For me, it was Mac. And make sure that you use Python version 3. So there's 2.7, 3.7. Make sure you use version 3. I just did this a couple days ago to make sure it all worked, so I'll cancel that. I already downloaded it. And let's see. So I ran that, and here I have Anaconda Navigator. It has a few more tools than we need just to run this Python code. But when you open Anaconda, you'll get this whole list of possible tools. And you just want to focus on Spyder. This one, it's the Scientific Python Development Environment. So I'll launch that. And as you can see, I do have the steps for the what I call the developer-friendly installation instructions on GitHub. I won't even go through those right now because we'll be focusing on Spyder, but just to point out that those are available, specified for both Mac and for Windows. Okay, so here's Spyder. I cleared out any project files, so it's pretty much just as you'll see when you open it. And so the only thing missing now is our functional flows calculator code. So the next step is just getting that code. So let's all go over to GitHub. Who here has been to the GitHub repository for the functional flows calculator? Anybody?
Yeah, I have.
Yay! Is this new for anybody seeing GitHub?
Not for me, but maybe for other people.
Okay.
Not for me, but it always probably scares me a little bit when I have to figure out how to navigate it.
Yeah, it's kind of scary. Okay, I'll give the 20-second overview of all you need to know for this project. So FuncFlow is living here in this repository. What you see here is essentially like a file system where all of the code files are living. Some of them are in more folders, some of them are just floating around like this. I think I have it already downloaded so you can see how it's the same thing that's in this file navigation. It looks, it's an analog to what you store your files in your computer all the time. But GitHub allows you to collaborate and share code and work on the same code together. So that's why it's here in this online format. And there's updates being made to this code all the time. That's just kind of the nature of a project like this. And so anytime the code is resaved with updates, it's called a commit. And you don't really, this is just for your interest, but you can go and look at all the fixes that have been made over time, mostly by Leo, a few by me. But the main point you should take from that is that if you download this code and work on it, and then you open it up 3 months from now, you should probably re-download it so that you have a new updated copy. I think I made a note of that here. Update your version of the repository periodically. Okay, so what we'll do to get this code for ourselves is download the zip file. And so this will be all the files that you see right here. I've already done it, but I'll just show what it looks like. Here it is for the third time today, probably. And so you'll want to move this entire folder into a place in your navigation where you can find it easily. So I just moved the whole thing over into documents. So FuncFlow master. Master means that this is the primary working copy. This isn't someone's experimental working copy that they're messing around with. This is the master. Okay, so we know that this is living right here in documents. And now we can open it up in Spyder. So I have the instructions on how to do that. You go from projects to new project to existing directory. project, new projects. It's the existing directory. As we covered, it lives in documents. We'll see what happens because I think I already did this once. Well, let's create it. Oh, great. And there's the files that I had open 5 minutes ago. And in case you don't have that file navigator open, you want to go to View, Panes, Project Explorer. Okay, this kind of gets us set up to the point where we can run the code. Is this part new for anybody yet? Have you done this already?
I've done this already, but I think it's good review for everyone else.
Okay, yep. Excellent. All right, so what else do I have in here? Okay, running the FFC in Spyder. So if Spyder is not the only way you can run the code, so it's a little different in any text editor or developer environment, but there's this nice big play button that you have in Spyder, and so that makes it pretty simple. The first thing you want to do is go to what's called main.py. So this main.python file is like the launching point into entering all the code. And I mentioned that play button. So to run the code, you just have main open and then press play. And then where you're getting responses from the code is here in what's called the console. And it gives us this nice set of options to choose from. Let's start with just an example. I'll create an annual flow matrix. So I want number 7, so I just press 7 and then enter. And then it will ask for the start date of the water year, just like when we put it on the online platform. So let's stay with the default, press enter. And then it allows us to choose from any of the reference California data to run. And so the data for the California reference gauges are split up into the classes 1 through 9. You can also just select one of the gauge numbers, or you can run all of them, which takes a long time, so I'd recommend just running 1 if you're experimenting. So I selected 2 for gauges, and it gives us this default gauge number, so I'm just going to run that. So I just press enter and it will do the default. And so now we're finally getting going running some of this code. So it spits out some of the information. This gauge is in class 1. Here's its USGS gauge number. And to look at our results, it's in what's called the post-processed files. And you can navigate to it directly from Spyder. It's in class 1. And there's a bunch of scary numbers. I kind of prefer to open it in my own file navigator because when I open it, it will just open right in Excel. Still looks scary because it's in scientific, so here we go. General. My Excel is being a little slow. What I'm trying to show is that, oh, there we go. The years are all showing on top. And this is just the flow being organized by water year. So every column will have either 365 or 366 values. So you could then plot with or play with this data however you want. It just gets it set up into a nice format. So let's close that. That was just for an example. And we can run other ones of those calculations too. Would it be helpful for me to show you where these gauge numbers are if you wanted to select other gauges?
Yeah.
Maybe? Yeah.
Okay, I'll just show really quick. So we're going to go back to eFlows.
Noelle, they may also want to know how to put in their own gauge data. so that they can work with the gauge that's not in the FFC.
Mm-hmm. Yeah. Was that Leo about to say something? Yeah, that part, I mean, we've had to work on with a case-by-case basis. We don't really have a streamlined way set up for that yet. Here, I'll just show first really quickly. You can look at any of the gauges available through the California reference gauges here on the website. It'll show you where they are and their name, and then this is the number that you would put in for the USGS gauge. To put in your own data, it's kind of getting deep into the files here, but we can just look here on our navigation. There are the pre-processed, the raw files. And so you could go in and then put your flow data into one of the flow columns for an existing gauge and just use it by that number. Maybe it'll make more sense if I open it here. So pre-processed, oh, sorry, raw files.
Open the first one, Will, if you want to show.
Okay, that's the smallest one, right? So this is kind of the quick and dirty way to put your own data in. You could just say, let's call my gauge 1141310. So just remember that number and then go in here and just delete out what's already here and put your data in. And you would also have to change the dates to align. So that's probably the most simple way while using the Python code to go in and use your own data.
Yeah, I think that's totally fine. It's a work in progress, so that's obviously going to be updated eventually, but just so people can start working with it. Thank you.
Yep. Mm-hmm. Yeah, so the website is set up to do it for just the basic calculations, but if you're already at that step where you want to go in and start adjusting parameters on your own data, this is the kind of hacker's way to do it for now. Okay.
It works, though.
Yeah, great. If it works, that's what we're going for at this point. Okay. So I'm going to go next to how to adjust the parameters. Are there any questions, quick things at this point before I start diving into the parameters? Okay, I'll move right along then. So the parameters are basically the modifiable numbers that we've put into the functional flow calculator, where you can adjust how the metrics are calculated. And so if you have a time series of data that just kind of works differently hydrologically than the California reference gauge data we've put in, then you might want to start changing things around. So the parameters are, I'll show them in just a minute, but they're organized in little libraries of numbers by functional flow component. So there's fall, spring, summer, and the names are based on calendar type seasons, fall, spring, summer, winter, because that's the naming convention we were going by when we started this project. And so short of changing thousands of variable names, we've just kept them as that. Although you'll see in the functional flow calculator, their names dry season, wet season initiation. So that's sort of a product of the fact that the naming convention changed in the middle of the project. If you have specific questions about that, please don't hesitate to ask me. So we'll go look at those parameters. Here's some examples. There's sigma parameters sometimes, and that refers to the degree of smoothing we put over the time series. I'll show an example or two of that. Oh, whoops. And then I'll show where those parameters are actually being applied in the code. So let's go back into Spyder. Are grouped by functional flow component in the old naming convention. So there's fall, there's spring, there's summer. Does anybody have a question or comment at this point?
You cut out for a second. So were you just showing us when you went into the parameters file?
Oh, whoops. Yep. Okay. All right, is everybody with me now? Yeah, so I just opened params. I'm showing how they're split up by seasonal flow component. And there's all these numbers. They have descriptions for pretty much all of them. Something about Spyder like has made the line not line up with the right one, but this minimum flow rate, for example, corresponds to this comment. Don't calculate flow metrics if the maximum flow is below this value. So that's the example of something that you could change. And it's a little hard, I know, to understand what these numbers mean when you just see them here in this file. So the way to start really digging into it is you can, let's just copy this and then find exactly where it's applied in the code. So for this sigma parameter, one cool thing about Spyder is if you click a variable twice, you'll see it highlighted everywhere. And so there's sigmas of different kinds here and there. There's another sigma in summer, so we want to make sure that we find the fall sigma. And we can go to this find in files and then paste our value. And let's just look in the entire project and see what shows up. So here we're in parameters, there's sigmas all over the place. Then we can see that in the summer calculation, there's some applications of it. There's a bunch in spring, there's a bunch in fall. So because there's so many, it's probably helpful if we know exactly what file we're looking at. So here in the PowerPoint, I mentioned the utils folder. This is where the real meat of the calculations is carried out. So let's go to utils. Let's look at the fall flush one. So that's going to be calc fall flush pi. Then we can search this sigma variable just in this file. Click enter. So we can see the line is highlighting where it shows up, right? Does everybody see that so far? Okay, I'll assume you all see that. So here just at the top, this is where the parameter is being defined. We're essentially pulling it out of that params file and putting it into this code. And then down here, we can see where they're actually being used. So for example, we calculate the time series with this broad filter using this broad sigma. And so we have a little more information about these filters, but essentially a bigger sigma is going to make a smoother hydrograph. And I'll show a couple plotting examples. But this is just to show how you can search a parameter and then see where it shows up in the files. Does that make sense so far?
Yes.
Great, okay. So I thought I would show an example of modifying some particular parameters. Again, in the wet season initiation / fall flush. So we'll go to this file again, but actually before we go to the file, I want to go back to our documentation and just read about this function. If you're starting to get really confused about what's in the code, again, you can go to our documentation online and just read about it. So let's go to wet season initiation, timing. And this will show us the steps for how we calculate the timing. And the timing is sort of the most complicated function for any of these seasonal flow components. Once you have the timing, the magnitude is usually just whatever the flow rate is on that day, for example. So often what you'll be changing for functional flow component identification is in the timing portion of that component. So we can see that you first check if the data has more than the allowed number of none or zero data. For example, that's what it would be interpolating between. And so if you wanted to make sure that it will only run if there's no zeros or no missing values, you could actually change that parameter. So here we see the maximum zeros allowed per year and the maximum blanks allowed per year. So you could go in and actually change those values. Okay, let's go back though, see what else there is. You have to identify the start date of the wet season, blah, blah, blah. Okay, so here, this is where we start to look through the requirements for this calculation. The first one is that the timing is before December 15th, or sorry, this should say it's before the start of the wet season or before December 15th. So we together decided that this fall flush peak should occur in the beginning of the water year. If you wanted to change this value, we could actually go into the code. Here in our params, there's a date cutoff down here at the bottom. And this is the latest accepted date for fall flush, counting from October 1st. December 15th would be a value of 75. So if you wanted to do away with that altogether, you could just set this as 365, which essentially means there's no cutoff. If you only wanted to look within the first 2 months of your water year, you could change this to 60, for example. So that sort of thing. So I wanted to look at two particular parameters. One would be this cutoff, and the other would be the minimum flush threshold. Is everybody with me so far on what the wet season initiation is, what exactly we're working with?
Yep.
Okay, great. I realized I could even show a few examples. So here you can see where it's being identified across water years. And if you thought a hump like this was too small, you could increase that minimum flush threshold so that you won't identify the wet season initiation unless it's above this certain amount. So we can actually go in and play with that. Okay, so before we actually do too much messing around with these numbers, I'm going to just put this one back to how it was. Let's just run the code as it is and see what happens before we change anything. That's probably a good idea. So we have to go back to the main py file first, then press play. We have a fall flush calculation here. So press 4, keep the water year. Let's just keep working with one gauge at a time, and we can use this default gauge. Okay, it's running. It's almost done. All right, I'm just going to go through my file navigation back to post-process files. And here it is. You can see it's the most recent file at 139, result matrix. And so this is giving us kind of a composite view of the numbers that came out averaged across all of our water years. So we have the 50th percentile of the flush magnitude was at 11 CFS. We have the timing was on day 315. That's in Julian days. I like to always keep a bookmarked Julian date calendar on my bookmarks. So here, let me show. Day 315, it's actually 2 days from now. So that's when the fall flush usually happens in this gauge. So that's pretty cool. So these numbers give us some sense of what's going on. But if you're really going to be developing these values and changing them around and seeing what happens, you can imagine it's probably helpful to see a graphical output of what's going on. So in each of our utils calc functions, we actually have a plotter function in here that's just commented out for most of the time because we don't want it to like go and produce thousands of plots unless someone actually wants that. So what I'm going to do is uncomment those plotter functions so we see what our results actually look like. So we're going to search plot in this file. What's up here, import matplotlib, that's a dependency. We're going to need this library for the code to run, so we'll uncomment that. Then we have this plotter. Let's make sure this is for the right function. It looks like it's, yep, just calculating fall flush timings. This is where the function is defined. So let's go back down there and uncomment this plotter function. This is actually for the return to wet season. As you can see, it's defined and then named. So we're going to skip over that one for now. Here we go. This is where we want to uncomment this entire thing. You can see it's been commented with this comment block. So I'm going to highlight the entire thing. And command 1 is my Spyder shortcut. Unfortunately, I have to go and actually push all of these lines over a little bit. This is the kind of thing that happens when you're developing code. So if you have a problem just like this, feel free to let us know, shoot me an email, and I'll see if I can help you push around spacing and indentations. Let's see if that fixed it yet. Let's see. Okay. So I think, sorry, bear with me for a second. I actually had to do this when I was going through this myself a couple days ago. I should have just kept this version for you all instead of downloading the code from scratch and running through it with you, but this at least gives you a sense of the kinds of things that can come up. So let's save. Okay, I think we saved our plotter function, so it'll actually work now. And you can see some parts of this are commented out. So you'll need to spend some time looking through and seeing what these variables actually align with. But I kind of know what's in here, so I'm going to comment out a few of these things. I'm going to make sure that we actually do plot our fall flush start date, and we might as well plot the dates for the wet season as well. So let's just see if that works. Whoops. I'm going to go back to main.py, press play, fall flush. And so if this works, I should get a whole bunch of plots showing up. Okay, hi again, everybody. The second half of our first webinar got cut off, so I'm just picking back up where we left off at a later time. And here we are. We're still modifying the FFC calculation parameters in wet season initiation. I've showed you where to find the file and the parameters. And now we're going to run the calculation with the plots, with all of our parameters in their default state here. So we'll go to main py, select fall flush, and our default gauge, and see how the plots turn out. Again, this is where I went down and uncommented out the plotter function and the relevant lines that I want to see show up in the plots. Okay, here they are. So I have a blue line, which is the raw flow data. You can't see it very well because over that is a fitted line with the smoothed or fitted data, which is very nearly matching the trends of the raw data. We have this red line going across, which is the minimum flush magnitude. So if you go back with me to params, you see the minimum flush threshold is 1, and this is the minimum allowable magnitude threshold for the fall flush flow. We also have this blue line that shows up whenever there is a wet season initiation. And so that's the timing on those years that we do have the wet season initiation. So you can see in this final plot that outputted, there was no wet season initiation. Here there was one. We had one in this year as well, and in a few years back. So now I'll show how we can change parameters, and that will actually affect whether or not we have a wet season initiation in each water year, and if so, where that occurs. So first I'll change that minimum flush threshold and see what happens. Currently it's set at 1 CFS, which the project team decided was still an ecologically significant amount of flow in most streams to see a difference. But perhaps we're working in a stream system where we want it much higher. So let's just put 15 there and save that. So again, we'll see this red line raise up. And so here are water years where we have a flush. In this third water year, we probably won't see one anymore once we increase that flush threshold. So let's go back and run the code again. Okay, our plots are generating. All right, you can see how that red line is pushed up to 15 CFS. So there's certainly no flush happening in this year. We still get the wet season initiation in this year, although it was originally happening at this smaller peak, but now it's picking up this much larger magnitude flow. And of course, in this third water year, we've increased it so that we don't see a flush in this year either. Another thing that we can change to affect where the flush occurs is by changing the degree of smoothing of the fitted line. It's this orange line which overlays the raw data. And if we have a larger degree of smoothing, even without changing the flush threshold, we can smooth out these small peaks, and so they might not be detectable. So let's go back to our params, and we will decrease our flush threshold back down to 1, but then let's also change the degree of smoothing. And so that's the sigma here. Right now it's at 0.2, which is very close to just representing the actual data, but let's increase that to something higher, like 5. Save that. And again, if you want to see where this is actually used in the code, we can copy this over, go to our file, put in, let's actually do that in variable file explorer. This one. Search sigma in our file. There's lots of sigmas actually. But here it is where we filter the data with a small sigma to find the fall flush hump. So we create this variable called filter data using the Gaussian filtering function with our original input data and this sigma variable. So here's just where you can see how it's set, and then this filter data is used throughout the rest of the code. So let's go back and run this again. So again, you'll see how this orange line will be smoother. It won't be right over our raw flow data. You'll actually see that now. And our red line's back down to the bottom. Okay, there you can see it very well. So the flush threshold is back down, and this orange line is now a smoother representation of this blue line underneath, which is our raw flow data. And here again, originally, we had seen the flush picked up on this smaller peak, but with our higher degree of smoothing, it's smoothed over. And so the wet season initiation flush doesn't happen until this larger peak. And here, even though this is a small peak, we still have enough there. So it would take even more smoothing to make this peak indetectable. And here, this plot had actually originally had a flush in this peak here, which was very small. And so this was smoothed out to the extent that you don't see this one occur anymore either. So that's just a few examples of how you can adjust parameters and see the results as you're developing this code for your own projects. I'm now going to show one more feature. This is actually new since the first half of this webinar, so we're pretty excited to show this. First, I'll run the main file, and you can see that there's this option number 9, which I hadn't covered before, which is upload files. And this acts pretty similarly to the website functionality, which lets you add your own files, except now you can actually play around with them in the code. So where we will work with this is in the file navigation. So I'm going to open up my own file explorer. We'll go to where I have this project saved. And here's our project folder. There's 2 folders that you're looking for. One's user output files and the other is user input files. There's a README file in here. Let's just open it with a basic text editor. And this just gives us simple directions on how to enter a CSV. We have the headers, date, and flow, and the same requirements as are in the website. So we'll just do essentially the same thing. So I'm going to find some of my own flow data. I have a Consumnes River time series, and I'll use that as the example. Here it is, our sample CSV. This is the same one that I showed earlier. And let's just copy it and put it right into this user input files. Okay. So let's close this and run again. And now we're selecting option 9. Pick the file to upload. If I had multiple files, there would be multiple lines, but since there's just number 1, the Consumnes file, let's enter 1. We'll use the default start date of the water year. And our results are going to show up in that output folder. Oh, since I still have the plots running, it's also giving me a bunch of plots, but what I'm interested in is seeing the results in the output file. So we'll go back to my FuncFlow folder. Now this was empty before, but now I have 3 new files, the same ones as we saw from the website. And so the first one should be the annual flow matrix. We can just open this up and take a look. So here's our flow data arranged by water year. We have our flow results. These are our metric results arranged by water year. Again, you can look at the README file we have if you need more information on what these metric values mean. And lastly, the sample dimensionless reference hydrograph data, so I can plot these out and make a reference hydrograph. And here we just have similar information, just what's showing up in the output files. And so now this gives you the ability to put in your data here, put in your own data. And then, for example, if I was working in the fall flush, I now have outputs from the Consumnes River Gorge in that calculation. So I could continue changing parameters and then see those outputs either in the output CSVs I opened or in any plots that I opened like this. Let's go back to where we were in the presentation. So I've showed modifying the calculation parameters, also showed how to modify with your own data. And then finally, where to get help. So always check the documentation first. We have the documentation for the functional flow website, as well as the specific metrics definitions. We also have a bug report capability on the website. So if you see something that is incorrect, you can just go directly to that page. You can also find it from the bottom of the website here in bug report. Let's go there. And this will just send an email to Leo, and then he can resolve whatever issues you have. And if you have any questions, you can always email me. That's things about the metrics or the website or running the code. And either I can help you directly or can send your message to Leo if needed. All right, well, thank you very much for being a part of this webinar. I hope it was helpful, and get in touch if you have any questions. Thanks.